Okay, we are going to continue with chapter 4. The power and torque in synchronous generator. As we said before, synchronous generator is a machine used to convert mechanical power into electrical energy. So the electrical or the mechanical power or the input to the synchronous machine uh, provided by using the prime mover. So the prime mover will apply mechanical input to the synchronous generator, which make the rotor of the synchronous machine to rotate. And when the rotor of the synchronous machine is rotate, it will induce electrical voltage in the stator windings. And this stator winding, when connected to external load, it will provide electrical power. So the input power to the synchronous generator Pn is equal to tau applied times omega m. So the input power, which is the mechanical power, will equal to the applied torque, which is tau, the torque applied to the camshaft of the synchronous machine, times the angular speed of the machine, which is, we said, the synchronous machine, it only has one speed, no two speeds like in induction machine. So the synchronous machine, it has one speed, which is omega m, equal to the synchronous speed, omega m equal to omega s. So this is the input power to our synchronous generator, which is a mechanical power. Okay, this mechanical power actually after the loss of the mechanical losses from the prime mover and the rotor or the shaft of the synchronous machine will be deducted from the input power. The rest of the power, we call it the P converted, will be converted from the mechanical energy on the rotor into electrical energy in the stator winding. So the P converted here is the converted power, or the power will be transferred from the rotor to the stator. So the P converted will equal to tau induced, or the induced torque, times the speed of the machine, omega m. Okay, so the induced torque here, or the power, also can be represented by the value of the induced voltage in the armature winding, which is EA, times the current, which will be connected to the load, or will be taken to supply the load, which connected to the stator winding, which is IA, times cosine gamma here. So the cosine of the angle between the armature winding, or the armature voltage, and the armature current. Okay, why we have three here? Three because we have three phase. Usually the synchronous generator is consists of three phase, so each phase will generate EA, IA, cosine gamma. So three phase we have, that means we have the power will be multiplied by three. Okay, gamma is the angle between EA and IA. So it's the angle between, as we mentioned in the previous video about the phasor representation of the energy of the power. So there is angle between the current and the voltage, and this angle can be lagging, can be leading. But in the case of the generator here, I mean, depends on the load. So EA here, or the gamma, represent the angle between the voltage and the current of our armature winding, or armature the armature of the synchronous generator. So this is the power flow diagram, like similarly to the power flow diagram in the induction motor, but here it will be like opposite, because here the input is mechanical power and the output is electrical power. In the induction motor, the input was electrical power, the output is mechanical power. So here we have, this is input power, which is applied torque times the omega m. It's come from the prime mover. So when we apply the prime mover torque on the rotor of the, or the camshaft of the synchronous generator, there will be some mechanical losses, tray losses, friction and windage losses, and also core losses. So these three type of losses will be subtracted or deducted from the input mechanical power. So the rest of the power will be transferred from the rotor winding to the stator winding, from the rotating part to the stationary part of the synchronous generator. We call it P converted. So after the P convert from the stator from the rotor to the stator, or from the field to the armature winding, So there will be some losses in the stator winding. We call it the copper loss, which is I square R, depends on the stator winding resistance. Okay, so these losses actually will be deducted from the converted power, and the rest of power will be converted into the P out. Okay, so if the value of R here is small, that means the loss of copper loss will be small, so the P converted will equal to the P out. If this value of losses is small comparing with to the P converted, so the P converted will equal to the P out. So the P out here equal to Z3 Vt IL cosine theta. And why we have Z3 here? Because actually, as we said before, we have the connection of the winding of the stator can be delta or star, and depends on the type of the delta and star, there will be a difference between the line voltage and the phase voltage, the line current and the phase current. For that, in the P out here will be represent the V terminal times I load times the cosine theta, which is the power factor of the angle between the voltage and the current. Theta here represents the angle between the terminal voltage and the load current, while gamma that we mentioned in the previous slide is on the angle between the current of the armature and the voltage of the armature, not the terminal voltage of our synchronous generator. So the P out here, or the real output power of our synchronous generator, which represent the electrical power that we are going to take to our electrical load, equal to Z3 B terminal I load cosine theta, or will equal to 3V phase. What's the difference between this term and that term? Here we are talking about the V terminal or the V line, while here we are going to talk about the V phase. Here we are talking about the current or the load current IL. Here we are talking about the phase current. So they should be a different. If you just try to apply the form that we have about the delta and star connection, when we said the V line for the star is equal to Z3 V phase, and in the delta the V line equal to V phase, and for the current the I line is equal to I phase for the in the case of the star, and in the case of delta I line is equal to Z3 I phase. Okay, so this formula now represent the output power either based on the V terminal and I line, or based on the V phase and I phase. When we talk about phase, we must multiply by 3 because we have 3 phase, so it will be 3 V phase I phase cosine theta, and cosine theta represent our power factor. Okay, this is the real power, and the reactive power that you learned before during your electrical fundamental. We have three type of power. We have the apparent power, which is S, and it's measured in kVA. Also, we mentioned that one during our transformer when we talk about the transformer, and we said transformer always is rated of transformer represented by kVA or by the value of S. Then we have the real power, which represent the relation between the current and the voltage times the cosine power theta, which is the power factor, or the reactive power here, which is represent the imaginary part of our apparent power. So S equal to P plus minus JQ. So the value of Q here equal to Z3 V terminal I line sine theta, or 3V phase I armature sine theta. Okay, so this is the two formulas that we are going to use to calculate the P out and Q out, and the most important formula for the synchronous generator, because actually the output of synchronous generator is electrical power. So we need to know how much real power do we have generated from the synchronous generator, and how much reactive power. Okay, so the theta here is the angle between V phase and I armature, and not the angle between V terminal and IL. See, it's not the angle between V terminal and IL, it's the angle between the V phase and I armature. It means V phase and I phase. Okay, so as we can see here from this phasor diagram, which show you the difference between the angle theta, the angles gamma and the angle gamma and the angle of delta. Okay, so we have three types of angles here. It depends on between which voltage and which current. Since we have V phase, we have also we have EA, which is the armature induced voltage. We have the V phase, which is the voltage terminal of the armature or of the synchronous generator. We have IA, which is the current of the armature. We have I line, which is the line current. Okay, so as we can see from this formula, it looks like here we have the V phase is less than the EA. V phase is the voltage that we are going to take from the terminal of the synchronous generator for one phase, and EA is the induced voltage in the armature winding. So EA here is greater than the V phase because we still have some losses on the armature winding or the armature reactance, okay, or the synchronous reactance that we mentioned before. We said XS, okay. So the EA sine delta, if you apply the formula EA sine delta here, so this is the value of EA sine this angle here will equal to XS IA cosine theta. When we talk about this cosine theta is this small one. So XS IA cosine theta. So as you can, if you just apply, I mean from the triangular relation here, so you have GXA IA here, which is the, I mean the adjacent, opposite, and hypotenuse here. So XSA is the hypotenuse for the small rectangular here. So when we talk about small rectangular, actually we are going to talk about EA's or XS IA cosine theta, which is the cosine of the angle theta here. This is theta is equal to the theta on this small triangle. Okay, so from this relation later on we are going to calculate or to find the value of the power of the generator. Later on, if when we have some examples about this part for the power and torque in synchronous generator, we are going to learn how to calculate the value of EA, the value of V phase, and the value of real power and armature power, I mean reactive power. So in real synchronous generator here, machine of any size, the armature resistance RA is much smaller than XS. If RA, which is the resistance of the armature, is smaller than the synchronous reactance, then the value of the losses for the, as we see in the power here, we said here we have I square R. If this value is very small, so comparing with the value of XS, so the losses here of the copper loss will be neglected. So the P converted will equal to the P out. Therefore, the armature resistance can be ignored. Thus, the simplified phasor diagram of this can be, as you can see here. So the IA here, cosine theta, will equal to EA sine delta over XS. So as you can see from this, EA sine delta will equal to XS IA cosine theta. So IA cosine theta will equal to armature voltage sine delta over XS. So you can see this the new formula to represent the current times the power factor. So the real output power here, if we substitute the value of IA cosine theta in the previous equation here, so we have the equation said P out equal to 3V phase IA cosine theta. Now we are going to replace this IA cosine theta with the new value, which is based on the sine delta that we found in this equation. So we are going to replace IA cosine theta in that equation. We got B out will equal to approximately 3V phase EA sine delta over XS. This value EA sine delta over XS represents the value of IA cosine theta. So this will be the power here, or the output power in terms of the voltage of the phase, the armature voltage or the induced voltage in the armature windings, and the armature or the synchronous reactance of the synchronous generator. And sine delta here, delta is the angle between the V phase and the EA, or the phase shift between the voltage of the armature and the voltage of the phase or the terminal voltage. Actually, if we see here, The maximum value of the power for this or the maximum value of the power for what that we can get from the generator depends on this equation will be obtained when the delta is equal to 90. If the delta equal to 90 degrees, so sine 90 will be equal to 1. So the maximum power will be 3V phase EA over XX. But in practical, sine delta is very small, is between 15 to 20 degrees. So we cannot, or the synchronous generator usually cannot achieve the maximum power at the full load here. Okay, so we observe the electrical losses here since we said the value of the resistance of armature is small, so the P converted equal to the P out, and the delta here represent the torque, we call it the torque angle of the machine, or the angle between V phase and EA, between the voltage, the phase voltage, and the armature voltage or armature induced voltage. Okay, so this is will be the maximum power, which is 3V phase EA over XS. If you ask what is the maximum power that we can get from the generator, it will equal to 3 for the 3 phase actually. V phase, which is the voltage of at the terminal of the synchronous generator. EA is the induced armature voltage, and XS is the synchronous reactance of the generator.